And this is 2160, the lecture 7, and discrete time Kalman filter. So I guess many of you have already learned something about the Kalman filter. 2151, for example, they included the Kalman filter several years ago, ever since they've been teaching that. But I know a little bit more sound understanding of Kalman filter requires a little bit more background knowledge, in particular, random processes and quantifications of uncertainties. You know, these are fundamental to understand Kalman filter, which is not actually the scope of 2151. So, you know, we go, you know, surely deeper into the subject. And in 2160, you have already solved the context-oriented project 1, where you were exposed to random signals and correlation, you know, orthogonality among the signals. So you are ready to study this. And also, Kalman filter has it's very flexible tools. That's been extended in many, you know, important different directions. And also, it has been applied to the new important application areas of today's interest. So we start with some basic algorithms all the way to most advanced one. Yeah, in the following the 6 lectures. Okay, with that, yeah, I met the Professor Rudolf Kalman when he gave a talk at the Kyoto University. When I was a first-year graduate student there, and I remember that the kind of auditorium was fully packed. At that time, he was basically the you know, star, you know, who made Apollo moonshot and possible. So Kalman filter already gained a huge, you know, praises, acceptance, and by the industry, and that has made a very significant impact upon the national, you know, interest too. So that was actually 1960s. And MIT has been heavily involved in that. Kalman is actually, he received the master degrees from MIT. So in many ways, he's been involved. And the Draper Lab is part of MIT, where this, you know, Kalman filter was studied for the purpose of navigation. And extended Kalman filter, which we study next week, is basically, you know, was basically developed there. Over 50 years later, it has a still very renewed interest. Self-driving cars and simultaneous localization and mapping, or SLAM, heavily uses the Kalman filter and its extensions, right? So talking about the Kalman filter, the basic framework is, let's go back to this, you know, prediction error correction formalisms. So you have a real plant and you have a model, and real plant produces some measurement, and then model also provides some predicted sensor signals, white hat, based on its own models and the parameter values. And they make a prediction error, you know, correction over here with some gain. This error is fed back to the model rather than the plant. Now, you know, in the past, we saw the same type of prediction error correction model in conjunction with the recursive least squares, where we estimated parameters. Well, now we estimate the states, but there's no fundamental difference between parameters and the states, as we discuss later. So this particular paradigm, this framework, exactly applies to a Kalman filter. But a Kalman filter is much more actually sophisticated, and you know, one important part is that it is to quantify uncertainties and use the quantified noise properties for better estimate the state. So we consider two types of noise. One is to disturb, perturb the plant, like in a car running over some rough terrain, receiving some bumpy stuff from the floor. So that's actually process noise. And measurement noise is purely a sensor noise. When you take a measurement, it comes with some noise, and that's denoted VT. Distinction between process noise and the measurement noise is very important. They play the different roles, and then actually it works in a very unique way. So knowing on how they actually count into the process is very important. Now, this particular framework, I should go back to this. It is basically the Leuenberger state observer, as far as to estimate the state in here. It is actually covered by state observer by the Leuenberger. Interestingly, it was actually invented after Kalman Filter came out, several years after that. But I know there's no uncertainty quantification, that there are no noise applied to it, the deterministic system. But I know Kalman Filter exactly followed that, uses that structure. So state observer plus quantification of uncertainty produces the Kalman Filter, and then that can be extended in many directions. So this is a little, recap for most of you. It's basically a state observer. The plant model, plant model is basically, linear time-varying system. State transition equations, time at the t, xt, make a transition to xt plus 1 with the driven by input, the ut, right? Matrix vectors xt is n-dimensional and the ut is r-dimensional, and then matrix is a and b takes the consistent dimension. And then the output is also the linear equation, an output equation, or we sometimes call it the measurement equation. It's given by the functions of state, which is actually a linear relationship. HD is the matrix relating these two. Leuenberger observer is to actually create the simulator of this state transition equation up to this point, with some correction term. The correction term is basically prediction error on the negative feedback. And so this is the actual measurement YT, and then YT hat is the predicted value. The difference is the feedback with this gain L. If the system is observable, A and the H matrix satisfy certain conditions, then actually, we can guarantee that estimated state XT hat converges to XT. And convergence speed is determined by pole placement in the case of time invariant systems. So Kalman Filter uses this, kind of framework, but this gain L is to be optimized using a different metric. But anyway, so this observer, you remember that this is the true state. We don't know, inside of the plant XT, some cannot measure the directly, but we're building this kind of a model and the mechanisms to correct the estimation of XT. This estimated one converges to this. After converges, it goes together with the true state. So some signals which you cannot actually measure directly with some physical sensors, but with this observer, you can actually access and estimate that not directly measurable variables that has immense applications and importance. Now, I said that there's no fundamental difference between the parameter estimation and the state estimation. Here's why. So this one is basically the kind of state observer, also Kalman filter structure. It is actually feeding back the prediction error with this gain KT. Well, in a Kalman filter case, and we, does include this input UT, but this term is basically deterministic term. It's nothing really actually important for the purpose of prediction, because this is fully predictable. So oftentimes we set this one to 0 without the loss of generality. So we put this one 0. And so the difference is that the XT versus theta t, and this state transition is a special, is basically a generalization of this parameter estimation scheme. AT, which is to take any square matrix, is replaced by identity matrix, because in the case of parameters, parameter itself doesn't have any dynamics, but it takes the constant value, but it is unknown. It is unknown, but a constant. So it is I, the same one as before, right? But in the case of dynamical systems, it is to make a transition as dictated by the matrix AT. That's the difference. It's not very much in the fundamental. Now, Kalman filter is a very flexible tools, flexible framework, flexible methodology. And in the following lectures, we expanded in many directions. Today, we focus on discrete time Kalman filter that is applicable only to the linear time varying systems. And soon this Wednesday, we extended to a continuous time Kalman filter, which is called the Kalman-Bussy filter, and that's end up with the Riccati equations. And this particular form is very convenient for doing some more mathematical analysis and convergence analysis in particular. Now, one of the major constraints of the original Kalman filter is the assumption that the plant dynamics is linear. But I know it can be extended to nonlinear dynamics, so linear plant to a nonlinear plant. And that's extended Kalman filter. And then also important and these days people use is unscented Kalman filter, which is actually a better type of the Kalman filter that can be applied to quite a nonlinear systems. And another important assumption is that the sensor noise and the process noise both are Gaussian. But this particular assumption, the requirement, has been removed with the use of a Bayes filter, and that is most flexible in the sense that it's applicable to nonlinear dynamical systems with non-Gaussian noise. And however, this one is harder to implement, computationally heavy. So we use the type of Monte Carlo simulation that's going to be a particle filter, which is widely used these days. Okay, so formulation of a discrete Kalman filter. First item, which is most important, is quantification of uncertainty. Okay, we quantify both the measurement noise and the process noise with regard to mean and correlations. Now, we assume that the noise process is wide sense. It is actually a random process. It is wide sense stationary. You remember this actually in a particular terminology. So first of all, the mean of each noise, process noise and measurement noise, the mean is constant, and they and also we assume zero mean. And if not the zero mean, we just shift the origin of the axis to that one. So without loss of generality, we can assume that the mean is 0. And then also, we assume that signal is uncorrelated. Although, by the way, since the mean is 0, correlation and covariance are basically the same. So, we use these sometimes in an interchangeable manner. That may cause a little bit of confusion, but because the mean is 0, the difference is not significant. So one of the big assumption is this, uncorrelated noise. Oftentimes it is called white noise. White noise is basically coming from the power spectrum of optical systems. And we haven't reached the PowerPoint power spectrum yet. So after we reach there in the system identification section, we officially call this white noise. In the meantime, we call this uncorrelated noise. What I mean by uncorrelated noise is the following. This one is quite involved, so please look at this carefully. First of all, you just pick one noise that's actually measurement noise of VT, and pick one particular component involved in the vector VT, say VTI, and as far as you look at these signals, you look at the 2 time slices, here and here, and then we look at the correlation between them. It turns out that no correlation. That is the assumption in here. Even though this one is actually next time slides over here, one step forward here, there's no correlation in that. That's a very strong assumption, but we assume that. So the same ith component of this vector BTI and the time slice SBSI, there's no correlation between them. That applies to both measurement noise and the process noise W. Okay. Now, as I said, sure.
Do we allow correlation between components of the process or measurement noise?
Yeah, so that's exactly the next item over here. Okay, so we have a vector, the VT. So this one is basically a measurement noise. So we use multiple sensor signals like sensor A, sensor B, sensor C, each having basically a noise random process and a noise over here. So we have a vector for this representing the measurement noise associated with the group of sensors. That's basically the output. Okay, so now let's pick the 2 items from components from this vector. So this is the ith component and the jth component. Okay, we again assume that we have no correlation between different time slices, T and S. So this is time slice S. This is time slice, the T. There's no correlation between them. But there may be a correlation, at the same time, we have some correlation, which we'll actually talk about later, okay? Now, we also look at the cross-correlation between measurement noise and the process noise, okay? So this is coming from VT, and this is the WT. And then again, to look at the 2 time slices, T and the S. We assume no correlation. As far as the time slice is different, no correlation. That's assumption. And also the kind of a baseline Kalman filter, we assume no correlation between process noise and measurement noise. There's no correlation between them. Okay, so in a mathematical expression, VTI and WSJ, whatever the components you pick, basically, these 2 crossing between measurement side and the process side, no correlation. That is the assumption we make. So in summary, let's look at the measurement and the noise. So at the time slice t and the time slice s, if you write the product of column vector and then row vector, you can actually expand it to L by L components, and this is to cover all the combination within this vector. Okay. Now, interesting to note is that this diagonal elements, if t and s are the same, they are basically the variance of the signal strengths, in other words. And also, if the sensor signals coming from the same the sensors viewing the same point from the different angles, for instance, it is likely that some components and the other components at the same time slice, they may be correlated. Maybe I should show this guy. The same time slice, these 2 points, from 2 components of the sensor group, I and J, they may be correlated. So that is why we have off-diagonal terms here. As far as the T and the S are the same, they may have some values. Okay, so in equation BTVS, as far as T equal S, and this may take a full matrix, not only diagonal, but off-diagonal terms also involved. That's RT. But we assume that the RT, at least the this diagonal terms, are all non-zero and then positive. Therefore, RT is to be positive definite. As far as we have some actual variance here, all the sensor has some variance. That means that there's no perfect sensor, zero variance sensor. There's no such sensor is involved. That's the basic assumption behind this. Process noise too, we have, we can write it in this way. And then diagonal terms T equal S, it may be some variance, and it may take this kind of full matrix. But at this time, this is related to the state, and depending on the state variables and then process noise, variance QT may be only positive semi-definite. It can't be as positive but definite, but a semi-definite. That is the assumption. As far as T and the S are different, they are totally uncorrelated, so zero. Okay, one interesting case is that the process noise versus the measurement noise may be correlated. For baseline Kalman filter, we assume for all the T and the S, they are uncorrelated. However, think about the situation that the sensor is sitting on the car and the car itself is perturbed when actually running over some rough floor. Then it is conceivable that the VT and then the WT may be correlated. So we can actually relax the conditions by allowing VT and the WT are correlated as far as T and the S are the same. If T and the S are different, we cannot actually accept that. Must be uncorrelated for different T and the S. But at the same time slice, they may be correlated. And that is a case involved in the PS number 2, which I released today. Program 2 is a case where we have a correlation between measurement noise and process noise. The derivation is a little messy, and I will not do that today here in the lecture. That's your job and to walk out and there. But a methodology is exactly the same as you study from now. Okay, to finally, this is somewhat obvious but important assumption is that these actually process noise and measurement noise are additive noise, just added to the state equation and the measurement equation in this way. And then matrix GT, like AT, is to, BT, excuse me, like a BT, is to represent how process noise is distributed among the state variables. Okay. So now optimal filtering problem, and let's formulate the problem. So what we'd like to do is basically optimal estimation in the sense that the mean squared error of state prediction. XD hat is the predictions of which we like to construct with the Kalman filter, and XD is true state. The squared error, and you take the mean of that, is to be minimum. And we like to actually construct the filter to make that happen. And this one, we like to minimize this subject to the state equation with this process noise and the measurement equation with the measurement noise. And then WT and the BT have very extensive assumptions on correlation. Okay. Now we deal with the two questions. One is that we assume the noise distribution. We never talked about, up to this point, we never talked about the distribution, right? One-time slice. Basically, as random process is actually a collection of random variables, and every time slice is a random variable. And the random variable has a distribution like this. And if we assume Gaussian for the distribution of the process noise and measurement noise, that's actually case one. And then if we assume that the Kalman filter is the optimum filter, although Kalman filter looks like this kind of linear form, but I know no other filter which may be nonlinear can be better than this. It's among the linear and the nonlinear filter, the Kalman filter of this form is the optimum. The other one, which is actually interesting, the Kalman's seminal paper came out 1960 in the ASME dynamic system measurement control. Just 1 year before that, another author, published the paper, which is actually arriving at the almost exactly same Kalman filter. But then that one was actually based on the recursive least squares, and the assumptions are a little bit more restricting. So and that one was something like this, and assuming that the filter structure is linear like this, like a recursive least squares, okay, and linear, where the prediction error is fed back with the linear gain, and then actually corrected this one, right? So if we assume this mode, this actually linear structure, interestingly, Kalman filter is the optimum regardless of the noise distribution. It can be applied to a non-Gaussian one, but it's only optimum as far as we use this linear filter. So what we like to do today, I like to first assume this form, and then actually solve the optimum Kalman gain over here, and then basically derive the basic Kalman filter. Later, after we study the Bayes filter, we basically prove the optimality of this by assuming the distribution is Gaussian. And then that is the lecture schedule. So let's focus on this guy. Here we assume this linear form. Okay, the flow of the discrete Kalman filter algorithms looks like this. And you get the similar stuff before in the least square estimation. So up to time t minus 1, including time t minus 1, we have some optimum state estimate, xt minus 1 hat, okay? Whatever the things that happens here, we just did everything that we can do and then get the this best estimate. Now, Kalman filter is to update this one to the new one, xt hat. But before reaching this, it goes through two major steps. One is that, well, we need to actually compare measured output YT against the predicted output YT hat. So we need to create the predicted output based on the model and basically, the noise characteristics. So we take the basically expected the state transitions of this. This is nothing but just simulation, open loop simulation. No feedback is involved, just based on the knowledge about the process, which is described by state equations. We take the expectation of that, and that's actually one time step ahead the prediction, and that can be done with just simulations, right? And then we do have the output or measurement equation. So based on the state estimated, we can actually produce the predicted output, which is compared to the actual measured output. And the error is basically used for correcting the state. At this time, we have already created this prediction before actually assimilating this new YT. But with this YT, we make a corrections to this XT minus 1 hat. Why we have a two subscript over here? This indicates that this prediction is based on the estimate at the T minus 1. And the T minus 1 to T is based on the model. So in that, we use this notation. On the other hand, the XT, there's no slash T minus 1 is basically, this is the estimate at the time T equal T. So this process, XT minus 1 hat is updated to XT hat. Now here, we have two major processes involved. Blue block represent the operation before we assimilate this new measurement YT. So this actually in a state estimation is called a priori state before we get this guy. On the other hand, this red blocks indicate the correction after we receive the actual measurement. So in that sense, it goes a posteriori state after this new one. So blue blocks is called propagation, and red blocks, it's called an update. Okay, there's no correlation to blue state and red state, Democrats and Republican. Propagation of state, this may be easy. Okay, state the propagation. In other words, it is basically a simulation that can be done based on the state equations, right? As I said, so this is the state equation, with the random variables, the WT minus 1. This deterministic term is nothing, just adding this one added to this. So with that loss of generality, we set the UT minus 1 to be 0. So we just, eliminate this, okay? In real situation, you can just put it back and just, one additional deterministic terms is involved in this. But our major interest is evolution of XT perturbed or driven by this noise process on the noise, WT minus 1. Okay, so let's actually predict the XT based on this equation. We take the expectation, right? So expectations, we can take the expectation, skipping this, going this, and expectation can be taken separately over here. And the second term, GT minus 1, expectation WT minus 1, we have assumed that the process noise is 0 mean, so this one goes out. This term is basically expectation XT minus 1 is our prediction of state, which is given at the time T minus 1. So this one is replaced by XT minus 1 hat, right? So here's the actually prediction at the time T based on the T minus 1 state, and just simply AT minus 1 times X hat T minus 1. Okay, so now here we have a model, and then actually what we need to do is to make a comparison against YT. So YT hat must be produced, must be created internally. So here's things. So you know, as we know, XT hat T minus 1, you know, we can actually use the output equation, which is YT equal HT XT plus VT. It comes with the measurement noise, you know, VT in here. So if you, you know, take the expectation individually, this one again, it means 0, so we can eliminate that. So this is the only things that we involved. So this is now, we just get this, you know, a priori state estimation x hat t minus 1. So replacing this one by that, we get this expression. This y hat HT AT xt minus 1 hat is the one that is actually in here. This is to be compared against the actual measurement YT, and the difference is to be fed back to this. Okay.
Professor?
Yeah.
Question. So in the prediction equation for y hat of t, we use the state matrices from time t, like h of t, a of t.
Yeah.
When we're predicting x of t, x hat of t, we're using the state matrices from the previous time step. Why is there what is the reasoning for the difference there?
Oh, no, okay. Yeah, so yeah, yeah, that's a little bit misleading, yeah. So this is just a general case, right? General case, this is a true one, right? And what we have available for, you know, estimating this is nothing but, you know, this sense, because we don't know the XT, of course, right? So we have to estimate this. The best effort we can do is basically this guy. This is actually, you know, predicted the state at the t equal t, t equal t, conditioned by the state xt minus 1, conditioned by xt minus 1. But, you know, this one, this one is the best estimate available at this point.
I see.
Yeah.
And I'm wondering why we have a sub t minus 1 in that first equation for x of t given t minus 1. Oh. And then on the last line, we have a sub t.
Oh my goodness! This must be my mistake. I'm sorry. I make corrections, and yeah, sorry about that. So that equation, slide 15. Yeah, you know, a minus 1. This is my silly mistake. Yeah.
So it should be t minus 1?
Yeah, a sub t minus 1. Yeah.
And we assume that is known for all t.
That's right. That's right. That's actually process and knowledge. And we have all information about it. Okay.
I see. Yeah. Thank you.
Sure. Okay. So now state update. So update is, remember, then going back to this you know, red block. Okay, red block. You know, now we get the new measurement. YT comes in. With this, we like to make a correction to this, you know, best estimate so far xt t minus 1. Okay. So state update. Newly observed output, then predicted an output the y hat is basically compared, right? So that's the comparison here, and based on this comparison is to be updated. Okay, so now yeah, you know, we assume that this linear update to low, yeah, in this proof. So we basically assume this form, okay, this linear form. Okay, and then we like to find the optimum gain KT, which is called the Kalman gain, is to be you know, obtained, you know, so that this KT is to minimize the expected prediction error. Basically, that's actually posteriori, you know, prediction XT hat, because we should incorporate the measurement YT over here, and then actually repeat back this, and all you know, included in this, you know, XT hat must be the best estimate. The difference between difference from the true XT must be a minimum. Okay, in the, you know, expectation sense. So what we like to do is to solve this problem, argument minimum KT, and then this is actually, functions of KT, and we like to minimize this. Okay, now here's a very important expression that we like to discuss at this stage. So the effect of Kalman filter, okay? Yeah, so this is the linear update law we assumed, right? We use. And then now let's consider two types of prediction error. One is that this is true prediction error. This is after we assimilate the new data, and then xt hat minus xt. This is actually our, basically, the error we like to minimize. But in this process, after propagation, we got this xt hat t minus 1. Okay, this is based on the state model. Not yet we incorporated the measured output, the yt, but this is the best estimate that we can do based on the previous estimate, xt minus 1, and process model, right? And then this one is called a priori error before assimilating the new data, and then this is a posteriori error after assimilating that measurement, okay? Et and epsilon t. We deal with two prediction errors. It's a little bit confusing, but it's very essential to use these two. Okay, of course, these two are related because of this update law, right? So ET, the definition of this, by substituting xt bar, xt hat by this, it can be extended this way, right? By using equation 23. And then now yt can be further extended by using the measurement equation, htxt plus vt is a measurement of noise, right? So let's actually put together xt and the xtt minus 1 right here. And then also here, let's factor out kt, ht, put these two terms together. We get the similar term, xt t minus 1 minus xt. And we have the similar stuff here. Let's actually look at this. This is nothing but the a priori error. So replacing this by epsilon t minus epsilon t, we end up with this expression. Et a posteriori error is some matrix times a priori prediction error plus this actually again kt times measurement of noise, VT, because we introduced this here, so VT stayed here and then shown up here. Now, what is interesting here is that surely a priori error epsilon t is somehow attenuated by multiplying this gain I minus KTHT. It's basically smaller than identity matrix. By multiplying that one, epsilon t is somehow attenuated to get the ET, which is after assimilating this measurement, KT. But as far as we use the measurement, that comes with noise, measurement noise VT. So as you increase the Kalman gain KT too high, let me see, suppose this is actually, Kalman gain KT, right? And, if you look at the ET in here, as you increase the gain KT too much, and because of this, you amplify the noise too much. So it's pretty high, right? As you lower the gain, it's better, okay? Now, if KT is too small, this one small, however, this term gets smaller. So this matrix is getting closer to identity matrix I, which is basically no attenuations of epsilon t. So if k is too small, it's not good either. So going up this. So there's very much likeliness that there's some optimum gain KT to pick. That's basically the Kalman gain. So we make some trade-off between these two to find the best gain in between the two. Okay, computation of an optimal gain. So what we would like to do is to minimize this, and the KT hat behind this, it actually includes the Kalman gain KT. So we just obtained this ET equaled I minus KT, epsilon T plus KT VT, and we talk about the trade-off between the between these two terms, right? Now, from now on, we omit the t, time t, because that's a little annoying. So just a simplifying expression, we can write this. So what we like to do is basically this, et square. So et square can be written in a product form, and et is basically this guy cut and paste. This one over here with transpose, and the same one over here. And let's expand this. So, let's split this one and this one. First, this transpose times this, that shows up. Oops, no, I broken down the further. So distributing epsilon here, epsilon, and a minus kh epsilon. So first, first term epsilon transpose, and then pick up here epsilon, and the next one, actually, I pick up this one, and then this one, and the third one, this transpose times kV. So the first three terms is basically these three terms, and the last three terms are basically cross product between, for instance, epsilon times second term is basically given by this, and then you can find it it comes with the two, because we get the same terms that comes up, and we just combine. Okay, so this is just expansion. So now we take a very straightforward method. I would say it's a little bit brute force, but I know a very straightforward method. All we need to do is basically take the derivatives of this guy and set it to 0, right? So of course we have to take the expectations over here. So that's in here, right? So we take the expectation of all these terms. That's actually the function of gain matrix K, right? So what we like to do is to optimize this with respect to gain matrix K. So necessary condition for it, just take the derivatives with respect to K, set it to 0. Yeah, that's actually straightforward, but matrix, K has many components in it. So this is not actually scalar derivatives, but a matrix. We have done differentiation with respect to vector, but this one is a matrix. I said repeatedly, for this one, don't be scared. We just take the, element by element on the differentiation. That's true, but in the case of matrix differentiation, it's more involved. So let's actually take a little bit more systematic method. So here's the lemma matrix differentiation rules. So we actually take a little side step to create the lemmas and then rules, and then go back to differentiation. So let's first consider the situation that f is a scalar function. Here's the matrix K is sandwiched by A and B vectors, and creating the quadratic form like this. It can be expanded to double summations, right? Now, what we need to do is to differentiate this with the component of matrix K. So differentiating this, let's see, a component involved in this matrix K, let's say KPQ. What happens if differentiate f with respect to component KPQ? That's the case when actually I takes the value of P and the J becomes a Q. Only that the case, differentiating this with the K PQ is non-zero. And then that picks up the this A and B. A, I as P, and then B, J as Q. That is this answer, right? So, component is this. Now we put it into a matrix form, and this can be arranged this way. Think about an A vector column, B vector row, and if you pick the PQ components, AP times BQ, that's exactly this guy. So if you write in this way, this is to form a matrix, that we need. So the FDK equal column vector A and the row vector B. So if you see this form, differentiated in K, go to this directly, okay? The second actual rule is this case. Now G is yet another scalar function, which is actually, include K transpose K, and sandwiching this with the vector C and the B. Okay, if this is the case, if you differentiate it with respect to K, the answer is this. And this can be proven in the same way as I did above. So I just leave this one to your exercise problem. And the actual solution is basically written in the my lecture note, chapter 5. So please look at that. Okay, so if you see this form differentiate with respect to K, it is actually expanded to KBC transpose and KCB transpose. Okay, we got the two rules. And these two rules are exactly needed in differentiating this actually, E square. Remember that? Now we get this expression, right? This expression. We have K transpose K here, and also, K over here, and then so K is sandwiched by two vectors from both sides, right? So we can apply those rules. So yeah, D is, square dk. First, this one doesn't have any K, so forget about that. And then let's look at from this list, this guy, okay, singular K, and also this one is singular K. These two terms, we can apply the rule 1. Rule 1, remember that, singular K is sandwiched by two vector A and B, okay? So in this case, epsilon is vector A, and the B is, vector B. So when we differentiate this, it actually shows up in this way, 2 times epsilon A vector, and then the B vector, column vector, okay? So this one becomes this. Likewise, this one, B vector is now H times epsilon. So, we can write in this way, A vector, and then B vector transpose comes in here, okay? Likewise, rule 2 applies to these terms in the K transpose K, K transpose K. We have 3 terms, including a K transpose K over here. And then in this case, you have to expand it to 2 terms in here. For instance, applying this one to this, a long expression, but look at this. This term, this one is basically vector B, and this vector C is actually, transpose of this guy, right? So having that in mind, this one can be expanded to this. So starting here, first we put this K, and then a B, it's a H epsilon, and then C is also, and the same thing, but I would take the transpose, epsilon transpose, H transpose. We have 2 terms and the same terms over here, and then apply this rule in the same way for other part, we can actually obtain these terms, okay? So after this point is very, very brute force method, just obtaining the optimal value. Okay, now we should not forget about the expectation. This is the result we have obtained so far, but we take the expectation. In a sense, we differentiation, we took the differentiation first, followed by expectation. But expectation, differentiation, both are linear operations. You can swap the order. So after taking differentiation, let's take the expectation. So expectation to every terms involved here expanded this way, and set this one to be 0, right? That's actually a necessary condition for optimality. Okay, now what is important here is to examine these terms, okay? First of all, this guy, VT transpose expectation, what is this? This is a measurement on the noise vector, and it's, row vector. And this guy is basically RT, 2 time slices, so we consider T and S. Now both are T, the same time slice. It may have some variance, and then this may be full matrix RT, right? But this one we'll introduce a little bit later. Okay, so this rest of the term, you see this kind of term, epsilon times VT. VT times epsilon. So let's actually, examine this term, expectation, the product of epsilon T and then VT transpose. Okay, so this is a busy, slides, but I know, I think you have done some similar jobs in the context-oriented project number 1. So let's examine this. Okay. So epsilon T, by definition, it is actually a priori state estimate xt minus 1, right? Minus xt. Let's put in here, and actually divided and then this xt minus 1, we use this expression, right? We use this expression, put it this one here, and then divide it into 2 terms. Okay, so second terms is a product between Vt and xt, from here, xt over here. So this guy, we can further examine whether any correlation exists between the true state xt and then measurement noise Vt. On xt Vt, we can actually use this expression, state equation. So xt is now expanded into this 2 terms, right? 2 terms. And examining the correlation between Vt and the Wt minus 1, basically this term, second term, GT minus 1, it can be proved out because that's a constant, right? So it's not a random variable. So examine this. Is there any correlation between these two? W is process noise at the time slice T minus 1. And the Vt is basically measurement noise at the time T, right? We assumed there's no correlation between measurement noise and process noise, and further, these two are different time slices, therefore there's no correlation between the two. So we can basically conclude that this one is 0. And this guy, well, this time is already time T minus 1, and then Vt is going up to time T. Maybe xt minus 1 that would include process noise Wt minus 2, or Wt minus 3, so forth, but it doesn't actually include the something Wt, and also further, they are not correlated, right? So basically, there's no chance that these two are correlated. So this one also is at 0. Okay, so this other whole is 0. Likewise, this term, now the major difference is that this one is basically a predicted one. And this is a true xt, this is the predicted one. And in doing so, we update it, meaning that the measurement has been brought in. Measurement comes with the measurement noise. So there's some chance that the Vt and the measurement noise involved in xt minus 1 would have some correlation. Let's check out. So xt minus 1 can be expanded to this form, right? Because you remember that this is the way that we, updated the states here based on the actual measurement at the time T minus 1, right? So, why T minus 1 may have maybe perturbed by process noise, but so it can be written this way, right? HT minus 1, XT minus 1, plus VT minus 1, involved in here. But I know looking at the correlation with VT sitting here, this one is, interestingly, we have VT minus 1 VT. They are uncorrelated. That is the assumption we made, right? Every, different time slices, even though difference is just one time step over here, it's uncorrelated. So we can conclude this going to be, zero. The other terms are even easier. Say, and it comes from here, yt minus hat, vt. This is actually noise at the time t. This may include the noise in previous time, but there's no way that these two are correlated. The same reason, xt minus 2 vt, xt minus 1 vt, no way they are correlated. So it's all zero. So we can conclude that this as a whole is to be zero. This one is uncorrelated, zero. So with this, back to that necessary conditions for optimality, we got this expression, right? This is gone, this one gone, right? And then this is nothing but the, covariance matrix RT, which is given as a part of the quantification of the, measurement of noise. So this part is this. And, this one, we define this to be a priori, state estimation error covariance, because the epsilon t and epsilon t transpose, and that is defined to be pt t minus 1, because this one is actually a priori, error. Okay, well, let's introduce this variable here. So with this, and this, we can actually rewrite this pt t minus 1 ht transpose. And this guy, the same one, pt t minus 1. And then last time here, kt times rt. Now we factor out the kt over here. And this is the common gain. We are almost there. All we need to do is to solve this for kt. And then interestingly, within this parenthesis, these two terms, and we need to examine a little bit. We wish to take the inverse of this matrix, right? So we have to check whether it is singular or not. But good thing, RT is already positive definite. And if this matrix, it could be something in the negative, then it's bad. But at least this one is positive semi-definite. Remember that the definition of a PTT minus 1 is something like this, back-to-back, two vectors coming this way, right? And then basically, for HT and GT and transpose comes from both sides. This one is a symmetric matrix. And then you can easily prove that this guy is to be, positive semi-definite. So, overall positive definite plus positive semi-definite, this other whole becomes positive definite, which is non-singular. That's why we can actually take the inverse to it. So, taking the inverse from right, we get this expression, kt equal this guy, ptt minus ht times this inverse. And this is the optimum gain called the Kalman gain. That is the story. Okay, so now let me check your questions and if you have some. Yep. Hanjun, what would be an example of process noise? Okay. So process noise, Hanjun, my favorite example is actually a car, okay, driving on the rough terrain, right? So as you drive, something, tire experiences a kind of up and down motion, that can be a process noise, okay? And Brian, random walk in angle sensor. Random walk. Oh, you are actually, answering to the Hanjun's question. Yeah, that may be, yeah. And Charles, how is PT T minus 1 updated from time step to time step. Okay. So that's exactly the next slides. That's exactly the next slide. Okay, this is actually, we just use intermediate variables, so it's not the complete story yet. But I know, I hope, yeah, this is quite complex. So, yeah, yeah, let me just pull back a little bit. I think you have a little bit, confused. So we should go back to this, okay? It has, propagations and update, right? Before assimilating the new data or after assimilating new data, right? And then we look at the first, forward pass prediction. That's easy. Actually, based on the model, we predict the, output. And then, since our output, which we predict, is given by this, okay? And then state, update is a little bit involved. And then we assume this actually prediction form and a linear form. And then interestingly, this ET, a posteriori, after assimilating the new measurement, comes with two terms, and these two are conflicting to each other. Remember that. So there's optimal value KT to make the best trade-off between these two. Okay, KT shouldn't be too high, just amplifying the noise, or too small, not effectively reducing the error from a priori and error to a posteriori error. Okay, and we did some very straightforward method. We want to take the minimum of this by differentiating this. That's actually stuff. And but complex differentiation. So we introduce the lemma, and we apply that lemma to this at the end. We get that expressions. But here the critical things we need to evaluate in this term correlation between a priori prediction error and then measurement of noise here. And then we did a very extensive examination whether any correlation exists between the two. This is a very extensive one, but you can do that, right? So to put them together, we arrive at this Kalman gain. That's where we are. But this guy is based on this particular matrix PT-T-1, which is nothing but the displacement of this guy. And we need to have some algorithms to compute this, right? So here's the stuff. Recursive formula for obtaining PT-T-1, okay? Remember, this is the definitions, right? A priori error covariance can be computed recursively together with another error covariance. That's actually this guy. Posteriori error covariance, PT, that's expectation ET transpose. Okay, remember ET and then epsilon T are related through these equations, right? So this is actually one important equation we derived. So let's take the posteriori error covariance PT. That's actually this guy ETT. And then substitute this one into this. Now we have two major terms here and here, and let's expand it. First to this one, and then this one transpose. So you get this, and the epsilon T and the epsilon T transpose comes back to back, and then we can take the expectation for this part alone, right? And the others actually, cross term, includes epsilon T and the VT transpose. That's basically we proved that this one is not correlated, so just gone. So remaining part comes from KT VT, VT transpose KT. That's it's this term. So we cannot ignore this. In fact, this one again, this basically covariance matrix RT associated with the sensors. So KT and RT, KT comes out together with this term. This guy is actually PT-T-1. So look at this. What is this? This is the kind of a formula to obtain PT from PT-T-1. This is useful, but I know this one can be further simplified, because the KT involved here is actually Kalman gain. So we can use this, Kalman gain, right? And putting this one into this. This is a long derivation. It takes about a page. This is so actually long, so I want to do that and just leave it to you. But believe me, the result is this guy, the simple form. Okay, this is the transition from PT minus 1 to PT. So this implies that the a priori covariance is reduced by updating the a priori state estimation, xt minus 1 with the newly assimilated, measurement yt. So this one is reduced to this pt. In turn, a priori covariance ptt plus 1 can be derived from a posteriori covariance pt. Okay, once we know pt, from pt we can actually obtain pt plus 1t. And let's obtain this. And this one is associated with the this error at the time t plus 1, right? This is the, nothing but the definition. And then this guy, excuse me, first this one is expanded to this form by using state equation. State equation, right? Comes with the process noise GT WT. And putting these together, factoring out the AT, remaining XT hat minus XT, that's ET. So we can write this. And we do the same thing. Let's actually compute the error, covariance of the epsilon T plus 1. So we now know this, putting this one back to back and expanding, do the same thing. And at this time, we have ET-WT transpose expectation. And then we can evaluate that this guy is actually 0. These two are not correlated. This one is actually, you can do the same thing. So DIY, do it to yourself. I actually leave this one to your job. Then actually remaining part is PT plus 1T is actually this first term. This one is nothing but the PT, right? Sandwiched by AT and AT transpose counting here. And look at the, this term. What is this? Expectation WT transpose. This one is basically process noise covariance, right? At the same time slice, T, so, it has some actually, variance, right? And off-diagonal terms too have some value. So it's actually a full matrix QT. This may be, this is actually positive semi-definite matrix sandwiched by GT transpose. So this is the things. Yeah, we obtained two, formula. One is to obtain from PTT minus 1 to PT, okay? A priori error covariance to posteriori, error covariance in which this Kalman gain KT is to reduce this, covariance to this much. And once you have it, now this next stage is propagation. So with this, we can actually propagate one time step, further. It comes out with this expression to create the PT plus 1 slash T based on the PT. And then we get the update from PTT minus 1 to PT plus T. And then continuing this, you reset the T as a T plus 1 and repeat the process, right? So, doing this recursively, we can get all the time sequence of a PTT minus 1. So we can actually, create this Kalman gain starting from the initial condition that you have to provide the P1 slash 0. You can compute all of these. So in summary, Kalman filter comes out this way. Right-hand side is real-time computation. So you basically, before you actually assimilate the data, you have to, predict your expected sensor output, right? So in doing so, first we do this open loop simulation and to move one step further, then create the output by putting the bring in the output function, and this predicted output, the yt hat, is to be compared against the real yt. And based on that prediction error, we update the state. And after this point is xt minus 1. Now with this feedback, we update this one to this a posteriori estimate. Okay, this required the common gain KT, which is computed in the left-hand side. Again, given initial condition, we can compute the series of common gain by computing a priori error covariance PT t minus 1. Okay, so that's actually Kalman gain given by this equations, right? PT t minus 1, which in turn needing two steps recursive computation. This one is updating covariance from here to here, and then propagating. Oh, just the letters missing here. Oops. The propagating the error covariance from PT to PT plus 1 / t. Okay, going back and forth, and this one we can compute this. All the common gain can be computed. Interestingly, left-hand side, we do not actually need actual measurement, right? Actual measurement used on the right-hand side. So this must be done in real time. But left-hand side, everything is known. What we use here is actually process model, like a matrix AT, and then HT, and then a GT, right? But we don't use the, measurement. So left-hand side computation can be done offline, if you like. Well, of course, you can do it in real time, but you can do it in offline. This side is actually, you need to do it in a real time, right? So that's the structure. Now, this left-hand side computation, updating and propagating the error covariance, PT versus T/T minus 1, is very essential in this algorithms. And that can be actually, shown here. This is my last slide today. So, two steps involved, right? So one is actually, basically propagate the state and then estimate, create the predicted sensor output, which is compared to, against the real and measured sensor output, right? So this side. And in doing so, we create the, model actually, predictions needed. So based on the previous state, xt minus 1, we actually create the next time step conditioned by xt minus 1. Like a robot traveling from this point to this point in one time step. We have some baseline, state equations, so we can move from here to here, like equation of motions, okay? But it comes with some perturbation, right? Perturbation. So this is nothing but just a prediction based on the simulation, okay? So as you do this, basically, prediction accuracy, and this one is to be compared against the true xt hat, right? The error covariance may get actually higher. So simulation propagation, if I plot the error covariance against the time step, initially, if you apply this propagation, P increases in some way. Next stage, we got the new measurement that comes in. Based on this one, we can actually correct the state. State correction or update is to take place that is actually lower this prediction covariance from this level to this level. And that's actually stated here. So previous an a priori covariance is attenuated by this much. As KT is larger, the attenuation is larger. Okay, and then actually reduce this and PT, that's going down. And then again, moving to the next stage, propagate the state, and then prepare for the comparison against the next actual measurement during the process. A priori covariance increases, and then it decreases, increases, decreases. This is the kind of pattern it goes through. So we'll discuss this one next this Wednesday through more continuous time stuff, and then characterize the Kalman filter. So that is the things that I'd like to talk about today. It's very intense, but I know all very clean. And then I hope this is interesting derivations. Every step is very well, articulated the step, and then really makes sense, right? Again, confusing notations, PT versus PT minus 1, before versus after assimilating new data. That's actually one challenge, but I hope you can actually manage that. So that's for today. Any questions? Okay. Brian, and how do instabilities arise with the short to covariance update? We look at the kind of global properties, and actually, Kalman filter as it goes, further, we really discuss, convergence and stability issue. To update. Okay. I'll actually, we'll actually do something to make it a little bit, I posted the previous, the early version of the, I posted yesterday. Maybe you need to do it in a few more days earlier. Let me just do it. Is regulation for prediction output to Y and the Kalman filter for predicting the state X? Hanjun, what is your question?
So I'm just trying to see how they are connected, the part 1 of the lecture, the regression part, and this Kalman filter part, how they are connected.
Oh, yeah, right. So, outlook looks very similar, right? But both are actually a kind of linear feedback, right? Linear feedback. And basically, one very important point is that, Kalman filter, if Kalman, state equations having some parameters which are not exactly known, then that often happens, right? Some adaptive control framework. We are given some, state equations, but some parameters, something is not actually, exactly known. You can treat, such, parameters as yet another state, and you can actually estimate that state, which is actually treated as a constant but unknown parameters. So, Kalman filter is basically subsumes the parameter estimations, like at least the squares. But the concept and the mathematical framework is totally different, right? And the major part is whether you, quantify the error properties. Random process, error properties. And that is actually, not involved at all in the recursive least squares, right? So, metrics is totally different. But at the end of the day, both arrive at the similar linear, regression forms.
I see. Yeah, thank you.
Okay. Okay. So today's lecture is quite a, extensive, right? And then this Wednesday is even more, intense. So I will post the, the lecture notes and materials in advance, right tonight. Although I make the kind of, minor adjustment to my lectures until the last minute, so I have to post it twice. The final version will be posted tonight for today's lectures. But I know, at the end of the day, you have to check the, development of the, algorithms. And check the mathematical treatment on your own. But, just to get the key points from the lectures, what is really about and the kind of, basic concept behind it. Yeah. And the PS number 2, question number 2, problem 2, I hope you don't think that is nasty questions, but you need to understand all I said today in order to solve that one. And making a little change to the basic assumptions, you need to derive the almost all entire equations, based on the different set of assumptions that is actually a little bit, involved. But by doing so, you get a very clear understanding about this technique. And then optimization technique itself being used is just a very brute force and straightforward one. And after we go through, the Bayes filters, we revisit this part to make the more official proof for the Gaussian case. But the basic concept behind it, like update versus propagation, I like this proof because that actually articulate these two mechanisms very clearly. And then we use these two repeatedly, to extend the basic Kalman filter to more complex, useful cases. So we hope you see more on this. Yeah. With that, today's lecture is over. Yeah.
Hey, somebody just asked a question about PSET 2. And then also Nick sent out a message about something about this recitation on Friday being just a discussion and not about PS2. It was kind of confused. He said, sorry. Yeah.
So, PS2 has, and I posted the last night, didn't I?
Yeah, I saw it last night, but I think I might know what this guy's talking about. I tried to look at some other document, and it was saying something about being unpublished.
Did I?
Yeah, I saw the same thing too. Yeah.
Oh, okay. Yeah, please include the Nick in the conversation. He is handling most of the assignments and so forth. So, but please send a message to Nick and CC to me.
For anyone having problem accessing the problem sets, like it's saying it not being uploaded, if you go to files and then access it from there, it seems to be you're able to access it that way.
Oh.
So if you, on the left side of the Canvas page should be a tab that says files. And then when you click there and go to problem sets, then you can download it. I'm not sure why it wouldn't let me access it from any of the other tabs. Even though it showed it there, it just said it wasn't uploaded yet, but Canvas being, I don't know, funny.
Oh, sorry, this is the first time I'm going to use a Canvas, so I have not a really good, point of contact. But Nick, he's a computer scientist, so he should be able to handle that. Yeah.
Okay. Yeah. So is the PSET due next week or the week after? Because the email Nick had sent said we'll be discussing PSET 2 next week's recitation, so like next Friday.
No. PS number 2 is to be discussed this Friday.
Okay.
Yeah. Maybe that is a typo or something, miscommunication. So, this week and the following week, a little short lead time. Yeah, it is today, discussed on Friday, and the following Monday is a due date. So,
okay. So I haven't looked at the PSET yet, but do we know everything we need to do?
Yes.
The PSET? Okay.
Yes.
As of today. Okay.
Right. Only today's lectures. Yeah, not the actual Wednesday's lectures. Yeah.
Okay, cool.
Yeah. Okay. So hopefully you can solve it. Yeah.
Also, Professor Asada, so I think it says for the lecture notes for chapter 5, it says they're like not available. Would it be possible to email them out as a file?
Well, I did post it though.
Yeah. I just used the files tab that Jacob had mentioned. So I can see it, but then if you click it, it says this file is part of an unpublished module and is not available yet.
What?
I think the Kalman Filters module might not be published. So if you go and like click the publish
Is that right?
check mark, it should turn green.
That's shame. Let me oops. Okay, so let me change my screen share to there. Oh, can you see it? You can see the canvas?
Yes.
Yeah.
Okay. So this is my view, maybe a little different from you.
So I think if you click on that do not enter sign in the gray bar at the top.
Gray bar at the top? Oh, okay, sure. Okay.
If you click on that, that publishes the module, so everyone.
Oh, this is one I did not do. Gee.
One of anyone's canvas.
Sorry. So now you see everything, right? So yeah.
Yes, now we can see everything.
Okay. I'm so sorry about it. Yeah.
Thanks.
Yeah. To me, I worked so hard during the weekend and created all these, three materials and then posted. I thought that you were all happy with it, but I know. Yeah, this is one which I did not do. Yeah, we moved to part 2, so that's why I had to push this. Huh? Yeah. My apologies. Yeah. So whenever you have the troubles, please actually give us a feedback quickly. Yeah. So that's actually a shame. Yeah.
Thank you.
Okay. Thank you.
Really helpful. Thanks.
Thank you.
Thank you.
Bye.
Thank you.